Last time, in the white eye diagram video, I mentioned that there is no eye mask at the RX input, which is not true for some protocols, especially in the PCIe compliance testing of the stress eye calibration. Then, you might ask, why the TX output swing along with the channel loss was not enough? The short answer is the bit error margin to ensure the RX devices meet the required performance standards for reliable operation in high-speed data communication environments. In summary, the stress eye test is a fundamental procedure for ensuring that the PCIe devices can handle high-speed data transmission without errors, thereby enhancing overall system performance and reliability. Let's start to look at the TX specifications, and you'll realize that the TX eye mask might be more straightforward than the RX eye mask. As you can see, the TX output swing defines the required signaling margin, and the jitter defines the timing margin in most specifications. Then, combining both signaling and timing to generate the eye mask specification, which is the output of the series. So, most design challenges of meeting the specification are from the intrinsic impairments of the circuit itself, not from the outside impairments added. In addition, the eye performance is easy to observe and bounded during the silicon calibration and design verification. Unfortunately, if we look at the specification of the RX, we only define the input swing along with the channel loss in dB at the next rate of the target data rate. The design challenges of meeting the specification are not only from the intrinsic impairments of the circuit itself, but also outside impairments. In addition, the eye or bit array control performance of the inside signaling and timing is difficult to observe and bounded during the silicon calibration and design verification due to its time consuming. For example, to meet the target bit array at RX, some design challenges of the specification are from the external impairments input J-tau, RJ, SI-PI, interference, crosstalk, etc. So, it's difficult to constrain every impairment from the input. The RX could receive a different TX from different vendors in the ecosystem. What should we start with? Perhaps think about the RX link budget for 5 seconds. Yes, for the link budget in a 30 system, we start with the eye height margin evaluation, and we'll discuss the eye width margin in the next slide. Then let's start with the TX output swing, 800 mV peak-to-peak differential, and roughly 36 dB loss at the next rate. Then we have the CTOE and DFE to equalize the eye size over PVT. Then a worst case residual eye size shows 160 mV peak-to-peak differential inner eye height. Second, the random noise from the circuit would be 2 mV RMS. Under bit error equals 1e-12, the peak-to-peak noise would be 28 mV. Third, the residual offset after the DC offset cancellation could be 5 mV. Fourth, the SI and PI from the reflection, crosstalk, or supply noise would be another 10 mV. Lastly, the sampler sensitivity could be 10 mV according to the required timing and the clock-to-queue delay at the target data rate. Therefore, the overall voltage margin of the I high in the link budget is 107 mV. Let's check the link budget of the I width analysis in the table. First, we accept the total worst case 30% UI TX total output high pass filter jitter RJ plus DJ from most jitter specifications. Second, our RX EQ results shows the residual I-side only DJ equals 12% UI. Third, the intrinsic peak-to-peak RJ of the data path 2.5% UI for bit error rate YE-12. Fourth, the DJ from reflection, crosstalk, and supply noise shows 4% UI. Fifth, the simpler setup hold time may require 10% UI for needed arrival time before and after the data transition. Sixth, the intrinsic RJ for the recovery clock 3% UI peak-to-peak for bit error YE-12. 7. The intrinsic DJ for the sampling clock of the CDR's hunting jitter and supply noise introduced jitter will be 12% UI in total. Lastly, the half-rate clocking's residual phase error could be 2% UI after phase calibration. Finally, the total I width margin is 27% UI at bit error rate equals YE-12. Then, remember, we have the I high 107 mV and I width 27% UI. Do you think that's enough? Think about the uncertainty image for 5 seconds. Correct, that's not enough. Again, in the ecosystem, the RX should expect any unknown inputs, especially in a complex SoC. Again, the TX may meet the iMask specification, but the system still has lots of uncertainties to break the link. The RX must receive different TX in the ecosystem and work reliably error-free over different unexpected external impairments in the whole service system. To make sure the RX can work in such severe conditions, people define a stress I calibration so that all the link partners in the ecosystem knows the RX performance margin. At this point, you may agree with the motivation and please try to guess what a stress I could be. Correct. For the PCIe combined test, there is a comprehensive I high and I width stress I calibration procedure, which you could follow the instructions from the PCIe specification in detail. I found an open source document you can refer from the PCIe SIG, which should give you a brief idea of what it is. First, you must add the ISI impairments along with the RX behavior equalizer EQ from the software to open the I after the EQ at the TP2P. In the first step, we should also add TX FFE in the best settings for the EQ optimization. Then second, add the jitter in SJ and RJ to the TX output source and calibrate at the TP1 to make sure the right amount. Third, add noise in differential mode and common mode after the TX output source and calibrate at the TP2 to make sure the right amount. Finally, we must calibrate the I at the TP2 after adding all the external impairments to meet the iMask specification. For example, we may need to tune the TX generator amplitude and noise iteratively to get the I width greater than the 0.3 UI and I high equals 25 mV for PCIe 3 after the whole added impairments, which we can finally tune. After understanding the PCIe compliance test in the calibration of the I/I, do you see any issue? Think about the I's intrinsic performance for 5 seconds. Bingo! In addition to the link budget of I's intrinsic impairments we just talked about in a few slides before, we need to tolerate other external impairments from the input externally. For example, from the most difficult NRZ stress I calibration of the PCIe Gen 5, the I high is even only 15 mV after the calibrated I of the AQ. Therefore, we need to talk about all the external impairments into our designing budget as well. Here is the updated link budget with the stress I test at PCIe 5. Long story short, we can meet the link budget with the ISI only channel or input from our initial link budget. But after adding all the external impairments from the stress I test at PCIe 5, we violate the I width margin, even if the I high could be still enough. Please be advised that the I width was shrinking a lot, not just from the external SJ, but also from the vertical noise interactions. So, what should we do to reopen the I again for the stress I test? Think about the tolerance image for 5 seconds. Great. CMSI and could be the SJ1. Looking at the external impairments from the noise, you may realize that the DMSI is not something we could do from your Microelectronics 101. But you must be able to improve the DMSI, which is the common mode noise in an ideal differential circuit block. Similarly, from the external jitter like SJ at 210 MHz, that's almost impossible to track, and we may focus on the more tolerant SJ at 100 MHz if possible. But in most CDR topology, it might not be easy to have a wider tracking bandwidth than 100 MHz, and that's still nothing we could do. So, most of the time, we still need to further improve the RX intrinsic impairments like RX phase errors, CDR stability and latency, residual ISI, and even other interference from supply noise, crosstalk, reflections. Here are the summarized images of why the ecosystem needs PCIe compliance testing in the stress I calibration. All are about the performance margin to provide the link transmission robustly between different vendors in the ecosystem. Therefore, on top of the ISI channel, the RX EQ not only needs to equalize the most difficult channel like ballpark 36 dB loss at 16 GHz, but also needs to tolerate the additional noise in both differential and common mode. On top of the normal jitter tolerance, the RX must also tolerate the other SJ at 100 MHz and 210 MHz respectively. Therefore, the final calibrated I should be only 15 mV in I high and 30% UI in the I width after the behavior EQ as a reference. To make sure your design RX can meet the stress I test, the DUT's EQ must outperform the reference EQ and tolerate those external CMSI and SJL1. Also, we must minimize the RX intrinsic impairments as little as possible to gain more performance margin. From my experience, if the RX can pass the stress eye compliant test for the PCIe, then it probably could pass most specifications of other open protocol easily. Please let me know if you agree with my observations. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.